Okay, let's jump right into the presentation. Mm, so the webinar, this event title is Unlocking Cloud-Friendly Apps. We will have a look at cloud-friendly apps from both dev and ops perspective. And the subtitle was Introduction to Kubernetes. We will have Introduction to Kubernetes, very short introduction to Kubernetes, and we'll as well have a look at stuff like observability, um, monitoring, and so on. My name is Paweł Kołodziejczyk. I'm trainer here at Comarch Training Center, the organizer of this event. You can find me on LinkedIn and on GitHub. As you can see, besides that, I'm also a dev/ops on a daily basis, as most of us probably here. Okay, let's jump right into the agenda. First, we'll have introduction. One element of this introduction is called time travel. I will quickly describe how we approached designing and implementing applications years back and how we do that now. So we'll have a look how this changed over time. Then we'll define what cloud-friendly means. We'll try to define what that means, giving some examples, some characteristics of app, that if an app has those characteristics, then we may say, okay, it's probably cloud-friendly. So we'll try to answer what that means. We'll tell a little bit about the challenges that distributed systems bring, because they not only solve the problems, they also bring complexity, and we have to tackle that, and we'll tell more about it. Then we'll have short intro to Kubernetes and observability. By observability, we'll focus mainly on monitoring using Prometheus and tracing, distributed tracing using Jaeger with the newest OpenTelemetry standard as well. And there will be live demos. So it won't be boring. I mean, it won't be presentation all the time. We'll have live demos, so not pre-recorded, real live demos. We'll have a look how Kubernetes reacts to an unhealthy application, if it will be restarted or not. So we'll just wait and see, okay, is it restarted or it's not restarted? We'll have a look at some Prometheus metrics, some dashboards. We'll have a look at how distributed tracing works. We'll generate some traces, look at them in Jaeger, then generate some other traces and look how they differ from the previous ones. So, and at the end, there will be also live demo connected with advanced routing. We'll incorporate also service mesh Istio for that, and we'll route like 99% of the traffic to version A of the app and 1% to version B of the app, and we'll verify live if that really happens or not. Okay. So let me just quickly jump back to okay, I see we have lots of attendees, so probably all of you who wanted to join, you're already here. So going back to okay, I just have to leave full screen to go back. Okay, so we'll start with the time travel, and we'll start by describing how the app looked like in the past. So in the past, when you or your colleagues or anyone, when we tried to design and implement an application, it was usually just a single instance. It was scalable, but usually only vertical scalability was allowed. By vertical scalability, what do we mean? We mean if your app is running out of memory or out of CPU, then what we do? We add more CPU, we add more memory to the instance that is currently running, and thanks to that, it works again. Of course, if the instance is only running in a single replica, it's single point of failure, because if the only replica goes down, there is nothing else. Sometimes we had failovers here. I will mark this as FO, it's failover. We want to discuss if it's passive or active, but having those failovers, okay, maybe Sometimes it was not really single point of failure, but usually and very often there was no failover at all. And the apps were really dependent by the underlying operating system. And because of that, the configuration was very, very difficult. So if you wanted to deploy your app in the one environment, then in the another environment, you needed to prepare those environments, and it took time, it took money, it took energy. Like you needed like 2 weeks, 3 weeks to prepare something. Then you could go to client, okay, I can install now my application because all the dependencies are installed, but you have to spend 3 weeks installing those dependencies and preparing the environment. What was later? So later, containers came. And by container, I mean, by containers, usually when speaking about containers, you think Docker. There are also other players in the market, but Docker is, I think, the most popular, even nowadays. And if I would need to choose a single word describing containers, that would be isolation. So you can isolate your app from the dependencies of the underlying operating system. And you can, and another word would be the app is self-containing. So we can say that inside container, the app is self-containing, because what container is, it's not only the executable, the your app itself. Container is your app plus all the other files, all the dependencies, all the requirements that your app needs. Like if you have a JVM app, you have all the jar files included there. If your app needs to run some other process, some other program, it's already installed inside the container. So everything is packed into the container, and we can look at the container as something atomic. So we don't have only app, we have app plus something else inside a container. And thanks to that, we have solved some of the issues. So we are no longer dependent. There is no longer operating system dependency. It's solved. Why? Because all the dependencies are now inside the container. So we have a container. I'm drawing here. We have container. Inside we have our app, and we have all the libraries we need. We have everything, all the files we need. I will just type F, and this is inside the container. And this container, I will just mark it as blue. This, we can treat it as atomic unit. And because of that, the configuration is also easier, usually done by environment variables. But we still have other issues, other problems that are not tackled. We still have single instance. Okay, maybe it's now inside the container, but still it's single. So we have to scale the same way as we did before, and it's also single point of failure as it was before. So we solved some of the issues, but not all of them. By the way, if by container we mean mostly Docker, so this slide would refer to Docker, but not to Docker Swarm. Yeah, so on this slide, I tackle only containers by themselves. I'm not speaking about Docker Swarm, because Docker Swarm area spans more than just containers. Docker Swarm is, I would say, example of orchestration. Like Kubernetes, I would say that Kubernetes and Docker Swarm are competitors on the same market, right? And by introducing orchestration and Kubernetes as an example, we may solve much more of the issues you saw on the previous slides. So by automating some processes, we may now have more than single instance. And it's very easy. You just say Kubernetes, oh, please run this in 3 instances or 4 or 5, and it will do so. We can now scale not only vertically, so from bottom up. Yeah, so we not only can add CPU or memory to a single running instance. We can scale horizontally. So what that means, if you have an instance, imagine you're a startup, right? And you have your app. This is your app, and your startup works fine. then your product gains traction. So you're happy, of course, because you have more clients, more money, and so on and so on. But CPU is used. Yes, 90% of CPU is used. 90% of memory is used. You have to scale somehow. So previously, what you would do, you would add more CPU and more memory to this single instance, but you don't have to do that anymore. Now you can create second replica of your app, and now you have two that can handle traffic. If that's not enough, you can have three, you can have 100, and so on and so on. And Kubernetes allows you to do so both in a manual way and automatic way. There is something called horizontal pod autoscaler. So there is no longer single point of failure, right? Because if you have many instances and once go down, one of them goes down, you have the rest that can handle traffic. So we can solve now all of the issues mentioned at the beginning. So you see, it changed over time how we approach the design of deployments of our applications, right? Let me see if there are. By the way, if there are any questions, I will from time to time jump into the chat, okay, to see if there is anything new. If not, I will jump back into the presentation. Okay. So what you saw before was rather Kubernetes perspective. So Kubernetes allows us to run multiple instances. Kubernetes allows us to not have single point of failure, to auto-scale, and so on and so on. But we have to ask ourselves, okay, is it the only area we need to care about? Can we just, today, can we just convert everything that runs outside of Kubernetes onto Kubernetes and it will work just fine? It would be difficult. Why? Because the applications that are running in the cloud, they also need set of characteristics that will make them, we say, cloud native or cloud friendly. I mean, it became a buzzword, so you can name it as you want, but we want to have an application that when we put it on a cloud, like on a Kubernetes, inside the Kubernetes, we will benefit from the features that Kubernetes or some other tool gives us. So if we put an app into the Kubernetes that can run only single instance, because when you run two, it's crashing, then okay, Kubernetes allows us to run multiple instances. But we can't do so because maybe the app is stateful, maybe it steals some RabbitMQ and Kafka messages and process them not in order, and some business logic fails, and so on and so on. So we need to have an app that is cloud native or cloud friendly. And there is a manifest called 12-Factor. It was developed by Heroku. Interesting fact is it was developed before the era of containers. I mean, before the huge popularity of containers, and it's still relevant until now. I won't go through all that 12-Factor mentions. I will just choose a few elements out of those and just quickly describe them, as I may refer to them later during our event. But I strongly encourage you to visit this page yourself in your free time. I think you will not waste time there if you haven't seen this before. So let's just quickly go through some of the examples. So the point number 2 is dependencies, and number 4 is backing services. What does it mean? It means that dependencies should be explicitly declared. And with containers, it's very easy because all the dependencies you need are inside the container. So they are explicitly declared. Previously, without containers, if your app was dependent on something, you would need to install it on the target platform, the target machine, target environment. Now, everything is packed inside the container. But what do I mean by everything? Every processes, programs that your app needs, but without backing services. And what are backing services? Backing services, those are Kafkas, Postgreses, Redises, Mongo databases, and so on. So all those kind of stuff. And of course, it's not running in the same container as the app is running. It's something else, some other container, but your app needs to connect to it. And it should treat those backing services as the resource. So it should be able to quickly switch between one Postgres and another Postgres by having some environment variable. Then the next, as I mentioned, I will not go through all of that because you didn't come here to just look at me reading some documentation, but I will refer to this when speaking about Kubernetes later, about some of those. That's why I introduced it here. So processes, basically your app should be stateless if it can. I know not every app in the world can be stateless, but if it can, that's very nice because stateless app is very easily scalable. So if you have one replica of your app, let's say this is our app, and it's running out of resources, then you can run another and yet another and yet another. And if it's stateless, they don't store any state. They don't have any state. So those replicas, they don't talk to each other because they are stateless. And one replica is not aware of the fact how many replicas are there. How many neighbors do I have? No, I don't care. So this A doesn't care if there are 2 more apps or 3 or 100 or thousands of nodes. No, it doesn't care if it's one replica or 1,000. So it's much easier to scale your app if it's stateless. So it's worth to design your apps in a way that they are stateless. They don't, for example, have sticky sessions. You can have sticky sessions outside of your apps. You can move that responsibility to Redis or Memcache, for example, and then you can much more easily scale your app. Because if your app has some state inside, like imagine your the sticky session is implemented, so you have a session inside your app, and the request goes to this A, then the next request for the same user goes to another A, and there is no session here, we have a problem, right? Okay, someone can say, okay, I can apply some consistent hashing and so on. So each request corresponding to the same user will also always go to the same replica that has that session inside. Then the problem is solved, isn't it? We may say, okay, with this workaround, it may be solved, but we need to remember that in cloud, applications are ephemeral. So the average time they're running is much shorter than in the past. In the past, when you deployed an application into the machine, it was running there for a very long time, like sometimes a year or more, and without an interruption. And if there was something wrong, everyone tried to fix it because no one was certain if after the restart the app will run again. Maybe something wrong will happen. Here in the cloud world, we have much different approach. If something does not work as expected, what we do? We kill the application, we stop it, and restart. So we don't try to fix it, we just, in IT we say if something doesn't work, you have to turn it off and on again. And that's what we do in the cloud world. Yeah, we shut down and run again. And this can happen due to multiple reasons. I mean, even Kubernetes, you might have some hardware failure, software failure, your health check may fail, and even Kubernetes on its own with some add-ons can decide to shut down your application because, for example, there is no space for some more important app to be run. So it will just close this app and run it somewhere else. And because there is no space, there are really multiple reasons for which the app can go down and can be restarted. So this happens frequently. And because of that, as a natural consequence of this, we need to care about fast startup, graceful shutdown, and resilience to failures. We didn't have to before, because if you were running, I mean, if you started your app once per year, you could wait 10 minutes until it's up and running. Who cares if it happens once a year? But if you restart your app every day or several times per day on average, then you need to care about fast startup. Yeah. And by fast startup, what do I mean? I mean, when you start your app, I will just draw some timeline. So there's a T, it's a time. So here you start your app. Okay. You start your app. And when you started your app, usually it's not ready right away. It needs time. It needs time. And let's say right here, it is up and running and ready to handle incoming traffic. But what happens if an incoming traffic comes during this period? Then, for example, internal HTTP server is not started. Then the traffic will not be handled. So this is by fast startup, I mean reducing this time. Ideally to a few seconds, but the less the better. By graceful shutdown, what do I mean? It's a very similar concept to fast startup. So basically, an app and inside a container receives a signal from like Kubernetes or Docker, and it has some fixed amount of time. Usually it's 10 seconds. On Kubernetes, it's 30 seconds. And by that time, your app needs to go down, right? So I will draw another timeline here, this time for graceful shutdown. And at the beginning, your app receives a signal. And the signal says, please, dear application, please shut down. And how can your app handle this? It can just ignore it. Then what happens after 30 seconds? Kubernetes will say, sorry, you had 30 seconds, now I will have to force you to shut down. Okay, and it's shut down. But if your app really handles graceful shutdown, then what it will do, it will try to process all the requests that are currently in progress, try to reject all incoming ones, and just shut down. And usually that process happens within a few seconds, so happens before Kubernetes is forced to kill your app. We should avoid it. We should avoid it because there may be some leaks in resources if Kubernetes forcibly kills an app. So we need to care about those two, and I think I understand why. Why? Because we have more restarts. That's a natural consequence. Okay, so we've discussed a bit application perspective, and now let's talk a bit about the challenges that distributed systems bring to our world. So what's distributed system? So it's some system that is distributed. So we have many components. They are somehow connected together. Maybe those components talk to each other through some protocol like HTTP, gRPC, maybe through Kafka, maybe through something else. But we have multiple components. And each component usually runs within multiple replicas. Maybe they are spread across geographical zones, continent, and so on. So imagine there is some issue within that system. And how would you find that? Would you just look at all the logs? Like we have 100 or 1,000 of instances, and you have to look at the logs of each instance. Yeah, that would be really, really difficult and would be time consuming too. So what's the solution? The solution is, because it's complex, like distributed system is complex. It brings complexity with it. Okay, we can solve problems. We can tackle challenges we could not tackle before with the modern distributed systems, but they are much more complex. And to address those complexity, we, as IT guys, I mean, not exactly we, but the IT community, discovered a way how to tackle that. So we need a combined view. We need a single place where we can have a look at all of the components distributed. So we can have a look, we need to have a look at logs in one single place, at the metrics, at the traces. We'll discuss them more in more detail soon. So how does that compare to traditional systems? Then we had smaller number of instances. So there was no need for observability. There was no need for automation, for Kubernetes, because if there's only a single instance or a few instances, you can have a look at the logs manually, one by one, and so on and so on. That's why we didn't have all those tools in the past, because we didn't need to. Yeah. And now we need them. We had problem, so we discovered some solution. And yeah, to sum up some challenges, so distributed systems can be more efficient, scalable, and so on, but they are much more complex. And what are the solutions discovered? One of them is Kubernetes, example of orchestrator. Of course, we need to care about 12-factor principles mentioned before. Another solutions will be discussed later, connected with more of a observability. But now let's talk about Kubernetes. So what is Kubernetes? Now we jump into the introduction into Kubernetes, and soon after that we'll have first live demo. We'll have a look how Kubernetes takes care of automatically of your app by automatically restarting unhealthy replicas. So we'll make a replica unhealthy, and we'll just watch if Kubernetes will restart it. So, but okay, before jumping into that, let's maybe tell a few words what Kubernetes is. It's an orchestrator for containerized apps. So you need your app to be containerized before you can run it on Kubernetes. But if you have so, Kubernetes manages all the life cycle of your app. So you can tell Kubernetes, dear Kubernetes, please run 3 replicas of my app. Please assign those resources to those replicas. Please, in case when it's unhealthy, please restart it. Or if it's very, very busy, please do not send new requests. Please wait until it's ready to handle new requests again. Or you can say Kubernetes, dear Kubernetes, this app is much more important than the other app. So when you run out of resources, please make sure you evict those less important apps out of the cluster, and those much more important, those crucial for our business will still be running. Or maybe you want to auto scale if there is not enough CPU or memory. Maybe 5 replicas is not enough. Maybe you have you have some online shop and there is a Black Friday and you want to scale if you have much more customers there at that time. So maybe you need not 5 but 20 replicas at that time, and you want to use autoscaler for that. But in short, what's the Kubernetes state? Sorry, not state. Kubernetes task. Kubernetes task is to match the desired state that is described by us, by users. So we as a users, we tell Kubernetes, dear Kubernetes, do something. And Kubernetes, it has inside an infinite loop, and it checks the current state and the desired state. And if there is a diff between those two, it tries to apply necessary changes into the cluster to bring the current state into the desired state. Kubernetes itself is a cluster, so I will just quickly go with this architecture. I will not go into much details because I think it's not the goal of this meeting to go into the details. You just want to enjoy it, relax, and view some live demos that soon there will be the first one. So, but let me just mention that Kubernetes itself has components that are responsible for taking care of Kubernetes itself. Usually it's called control plane or master nodes, and it has components on which we run our app. So if you want to run your app, it will go to those regular nodes usually. As mentioned, I will not go into the details. I just wanted to show you that Kubernetes itself is also some cluster that has to be run somewhere, and we just need to keep in mind Why? Why would you ever want to run Kubernetes? So if you want to run Kubernetes, you probably strive for HA, which stands for high availability. So you want your apps to be highly available. So if one of the replicas goes down, there are others. So your customers are not affected. But you need to also remember that always when you think about high availability, always you need to go one step down, in this case, into the Kubernetes level, and you need to make sure that Kubernetes itself is also highly available. Because if Kubernetes itself is not highly available, then it means the whole Kubernetes cluster can go away and everything on it also can go away. So it's good that if you have multiple control plane nodes, if you have multiple worker nodes when you run your applications, you may also have autoscaler for the whole cluster. So there is not enough space. A new worker is being added. For that, you need your Kubernetes needs to be able to talk to your cloud provider API like AWS and so on. But just mentioning that Kubernetes also some tool as an orchestrator that needs to run somewhere and also needs to be highly available. Okay, let's now jump into the most basic object type in Kubernetes, a pod. We will be running a pod soon in our Kubernetes cluster. So a pod simply represents a process or an app that's running in our cluster. I mentioned before when speaking about 12-factor that apps are ephemeral, and also pods in Kubernetes are ephemeral because they represent our applications. They consist of one or more containers. Each of the pod has its own unique IP address assigned. And Kubernetes scheduler decides where to run your pod. So if we quickly jump back into our architecture, you see you have multiple worker nodes on which you run your apps, and it's up to Kubernetes scheduler to decide where to run them. Of course, you can override in the behavior of scheduler or help scheduler with the decision. There are also other objects. I won't cover all of them here, but now we will try to ask this question. Can we trust our application? And how do we know if our application works fine? Let's say we have Kubernetes, we have our apps there, they are running. If you look at the status, it's running. Okay, then it's fine. When you look at the status and it says, oh, crash loop backoff, or it's crashed, it's failed, then what does it mean? If your app fails, it means it's not running anymore. There is a problem. We have a challenge to tackle because it's not longer running. But is there any good news out of that? Yes, it is. At least we know that something is wrong. So we are aware of that. Yeah. If it's crashed, it's not running. Oh, we see it's not running. We look at the status and it's not running. But if it still works, we can ask ourselves, does it work fine? Or maybe there is some hidden failure inside. There is something wrong, but we just don't know. That's worse. Yeah. I think in my personal opinion, if your app crashes, you know it, you are aware of it. If there is some hidden failure you don't know, your app is still running. From the Kubernetes perspective, everything is fine. Process is running, it's green, it's ready. But when you send a request to your app, you get internal server error. Next request, internal server error, and so on, and so on, and so on. So this is how our app looks like from Kubernetes perspective there. Then there is some fire inside, there are some issues, but Kubernetes looks at this app and okay, it's fine. How can we tackle this problem? With Kubernetes, we may apply probes also sometimes we refer to them as health checks. They are executed periodically, and this will be the topic of our first demo today. The health checks, what they do, basically, Kubernetes periodically asks our app, are you healthy and are you busy? Or just one of those. It depends how you configure your app. And if it detects, oh, app is not healthy or app is busy, then it waits until there are three consecutive failures, and then it takes action. In case when Kubernetes asks our app if it's healthy and it's not 3 times in a row, then it's restarted. In case it's busy 3 times in a row, it's not restarted, but it is marked as not ready, and it does not receive any new incoming traffic until it becomes ready, not busy again. Okay, and this is the demo time. So I will just stop sharing this screen. Yeah, let me see if there are any questions on the chat. But I know you're waiting for live demos. Yeah, that's what I'm waiting to for. Let me see. Yeah, I have everything prepared here. Let me now switch to the okay, to the terminal window. Share up screen. I can share the whole screen. I think it will be easier. Okay. Yeah, you should be able to see the empty terminal, and I just want to show you that I'm running a bunch of pods here. Just for confirmation, please leave a message on the chat that you can see my screen, you can see my terminal. I'm switching between WebEx. Oh, thanks a lot. Okay, I see. Yes. Okay, no. So we can go back here. I will talk a few more words about those apps that are running here, but for now, I just want to show you that we have multiple apps running here, even some Postgres, some order applications, some products, some Vue with different versions. This 1, 2, 3, it means which version the app is running, and each of them, when we look at the something called Kubernetes manifest, so kubectl get PO, let's just look at the random pod like this workshop view 1. In the when we look at the manifest in the YAML format, I won't go into all the details here, but I just wanted to show you that I have single container defined here. Here is the container, and there is something called liveness probe here in this place. Can you see? You should be able to see. Failure threshold free. This means, and this is our are you healthy? This is where our are you healthy is defined. And we say to Kubernetes, if there are 3 failures in a row, then it should be considered as failure. We show Kubernetes where is the path. What is the path to look at when doing this request? It's the endpoint /liveness, and this endpoint had to be prepared by the developer developing this application. So in this case, by me, because I wrote this application. But if you want to apply liveness probe is health check for your application, you need to expose somehow to Kubernetes a way to check if the app is healthy inside. And what it's doing inside, it depends on what the developer decided it has to do. So, for example, it can check if the connection to Postgres is still valid. It can check if connection to Kafka is still valid, and if not, this endpoint will fail. So what this endpoint does internally, the possibilities are endless. It's up to developer. The port is HTTP. I've defined it above. It's 8080. Initial delay seconds means we don't ask, are you healthy within this period? Then period seconds means, okay, we ask every 20 seconds. Success threshold means 1, means if there are 2 failures and 1 success, then we have to count to 3 again when counting failures. So 1 success means Kubernetes forgets about all of the previous failures. And the timeout is 1 second in this case. So you see, we have it defined. Now, let's go back. I have an alias for kubectl, which is a command line tool for Kubernetes, and I will just type K, and I will just list the pods again. We have a bunch of apps running here. And I have this app written in a way so I can, on demand, turn it into unhealthy. But first of all, let's have a look what is the IP address of this app. I mentioned, let me make this a little bit okay, like this. This is the IP address of my app, and what I can do, this app is not exposed directly also of the cluster, so I have to send the request to this app from another application running inside of the cluster. So what I do now, I will, from this spot called the BBC, is just there is simple app which has a curl installed inside. I will just call curl, and I will just use this IP address on port 8080 / liveness. I can also take JQ, and as you can see, this is what this app returns. This app is saying, okay, I'm fine. And if you look at the HTTP code, it's 200, it's okay. What I will do now, I will manually toggle the switch, and I will make this app unhealthy. That's how I designed this app, so I can do it by hand. Okay, and now when I ask again, are you healthy? It will respond with an error, you see, and 500 code. So from now, this app, this workshop v1, is failing liveness probe, because what we did, I mean, this request, that's exactly what Kubernetes does when it asks, are you healthy, are you healthy, are you healthy? And we have an error, and it's 500 internal server error, HTTP code. So after some time, what we expect this column restarts, and this counter for this particular pod will increment to 1 if the restart will happen. And let's see if this will really happen. And look, I just listed all the pods, and as you can see, it is really restarted 4 seconds ago. So it really happened. So our app started failing the liveness probe, and Kubernetes decided, okay, I got 3 consecutive failures, I have to restart. And look, it really, really happened. By the way, why it's not ready yet? Because there is also readiness probe there inside the app, and there is also a parameter called initial delay seconds, so app is not instantly ready, but after some time, look, we have our app again, and where we now, when we again do this URL, you see it's okay again, because it's restarted and it's again in a good state. So we've just tested Kubernetes in this live demo, if it really restarts the app that is unhealthy inside. And as you could see, all the time the app was running, the status was running all the time. Imagine we didn't have a health check. And imagine some real life scenario, like you have an app that is somehow disconnected from Postgres, but the Postgres database is still up and running. But internally, your app cannot make any insert or select statements into the Postgres. And you have to restart it. But from the Kubernetes perspective, it's up and running, and you don't have health check, you don't have liveness probe. Then it will remain in a broken state. With this, you can restart it. Okay, I will stop. Oh, I don't have to stop sharing, actually. I can just go here. why Vue is restarting. Oh, sorry, I now can see. How can you say? Oh, so I'm now answer the question from Victor first. How can we send the request? So this app is not exposed outside of the cluster, but we have this BBC also running inside of the cluster. What I did, I sent this CURL request from within BBC. So what I did, I've logged into the BBC pod, and from inside, I've sent the CURL to the other pod, workshop Vue. And that's why not BBC is restarting, because I've used BBC only as a proxy, I would say. So I've logged into it only to be able to access this workshop Vue. And I think that this also should answer this also should answer. I don't know why I cannot switch. Yeah, another question. Yeah, so maybe the question from Victor was, how can you send? So you need to expose your app outside, but how Kubernetes does so, Kubernetes does so internally. So Kubernetes automatically does so every, in my case, 20 seconds. It's not, of course, outside of the cluster, but if you want to expose your app outside of the cluster, you can do that with service of type node port or with different kind of ingress types. Yeah, because you may have multiple ingress controllers, but I won't cover this topic now. But yeah, you can expose your app outside. But what I did not send the request from outside. I send it from within the BBC. The BBC stands for BusyBox with CURL because it's a BusyBox. BusyBox is okay. Maybe this will be oversimplification, but it's a simplified Linux with some commands with the CURL installed. So I have CURL installed there inside the BBC. Okay, let's go back to our presentation. Okay, and let's ask another question. Is that enough? We have health checks. We have auto-scaling. We have Kubernetes with all its benefits and so on. Is that enough? Maybe yes. It depends. It depends is always the right answer to every question. But maybe we need more. Maybe we need metrics, logs, traces. And all of them are aggregated under a single term called observability. Sometimes some people add another elements to this, like security and something else. So you may, if you read the web, the internet, you may find different descriptions of what observability is. But everyone agrees that at least logs, metrics, and traces are there. But someone can add more. Those are a few logos of what we'll be using today. So we're using Kubernetes, obviously. You did. We use Containerd, is the runtime for containers used within Kubernetes, because we have containers. We need some container runtime in order to run containers, and Kubernetes uses by default Containerd. OpenTelemetry is the standard that tries to define a unified way of for metrics, logs, and traces. We'll use Prometheus soon. Grafana we won't show today. Prometheus will be enough, but we'll show Jaeger and also Istio that will help us route like 99% or arbitrarily percent of requests into the specific version of the application. Okay, and let's now talk a little bit more about the workflow applications that I used before, and we'll use them also now. So as you saw, there is something called view, order, and product. Those are very simple apps that are responsible for managing orders. And you basically have two services, order and product. each of them has its own Postgres database. It's the same Postgres instance, but within that instance, you have two different isolated databases. And inside the order service, you have access only to product IDs. You don't know if the product number one is an apple or banana or something else. You have just the ID. So you need another service called view in this case. And this service called view is responsible to take the orders. Inside the order, it has the IDs of products and fetch the relevant products also from product and put that all together to display the list of orders to us. And that's what we'll be doing soon. So that's basically the summary of what I just told. In case of products, you will have product name and some optional fun facts. For orders, you will have order date plus product IDs only, plus some remarks for the order, and view combines all of that together and also is responsible for some initial load with random data. That's what we will expect from the app. As you can see, we have a list of products for some order, and you have a name, fun fact number one, and additional fun fact. And this will change when we change the version of the app. So, for example, version number one will not print fun facts at all. Version number two will print single fun fact, and number three will print two fun facts. So the versions will be different. Will have different behavior, and at the end of our meeting, I will show you that when I change the advanced routing mechanism to forward more or all traffic to some specific version, you will see more fun facts and less fun facts when asking about this. But all of those apps, what's really important, they also expose metrics in Prometheus format. So there will be also Prometheus running in our Kubernetes cluster, and it is. And also each app sends traces in the OpenTelemetry standard to the collector. In our case, the collector is Jaeger. It supports OpenTelemetry. By the way, OpenTelemetry standard, I said it covers all of the logs plus metrics plus traces. But in case of tracing, I think it's the most major part of this. So the other two parts, metrics plus logs, they are evolving, but for traces, I think is quite in a good shape now. The source code for all those apps that I share here is available on my GitHub. I will share the link at the end of this event. You will be able to go there and run it through locally, even through Docker Compose with Jaeger, with Prometheus. Of course, you won't have access to all I show here to Kubernetes, but some local, so you will be able to get a taste of what I'm doing here by going there. Okay, so I mentioned there is Prometheus, there is Jaeger. So in case of Prometheus, it's a monitoring server used a lot in the industry. It has a very large community, can be installed on Kubernetes, outside of Kubernetes, so you basically don't need Kubernetes to run Prometheus. You can write Prometheus not having Kubernetes at all. And on Kubernetes, you can install it in many ways. It's a pool-based system, at least until now, in version 2 point something. In version 3, it probably will be compliant with the OpenTelemetry standard I mentioned before. Also, will be able to handle push-based, but we'll see. It has dedicated query language, PromQL. I will show you some example. I won't go into the detail here because during this event we are unable to catch all the details, but you will see some graphs showing that something is going on inside the app soon. There are different components of Prometheus, but we'll just use a single one today, the Prometheus server. You can also have rules and alerts. So instead of manually look at all those dashboards, you can have an automatic alerting system and send you an email or Slack notification or anything. This is basically an example of what we can get out of Prometheus. This is built-in Prometheus UI. Normally, in the production scenario, you don't use this UI, you have dedicated Grafana, but for the purpose of this webinar, we'll just use built-in Prometheus UI. It's enough for us. As mentioned before, OpenTelemetry is the standard. It's fresh and ongoing, but it's good for us that something like this happens, because it should be very easy for us to change the backend. Like you use Jaeger for tracing, it supports OpenTelemetry, and you want to switch to some other tool which also supports OpenTelemetry, you don't have to change the app. The traces are sent the same way as they were before, you just change the backend, and so on. So in our case, Jaeger will be used as a backend. It will collect all the traces that our apps will send to it. In case of tracing, yeah, we have more standards, but if there is new OpenTelemetry and it's quite mature, in case of tracing, we will use only this one. The different standards, they differ in a way how they pass, how they encode some metadata, some information about who is parent of whom, and so on. This is the example of what we'll be looking today. We'll send a request from one app to another, or from an app to itself, and look how the traces look like. So this is just a screenshot, but we'll have a look at this live now. Okay, let me just remove this full screen and see if there are any questions. Oh yeah, thanks Krzysztof for the link to GitHub. So I will not. I will paste it maybe at the end. All the links, including this one. Okay, so let's first, no, not this. Let's first go to the terminal, but this one. Okay, and I said to you, by the way, I didn't tell you one important thing. Don't believe me when I do something. If you have a question, just ask it on the chat to ask me to prove it, actually. Because, for example, I told you that each of the application exposes metrics in the Prometheus format, and I haven't shown you if that's really the case. So I will do that now. So let's do kubectl get PO. Let's list the pods with the IP address. And yeah, let's take random, because all of the workshop apps do so. I will take random workshop product 2, and I will do again CURL, but this time the endpoint will be /metrics. /metrics is the default endpoints where Prometheus will check in order to fetch the metrics, and there are some metrics. Again, we won't go into the detail. Don't worry. I will not describe everything that happens here, but there are some metrics. Yeah, that's what I wanted to prove to you. And also the apps. Let's have a look at the logs. kubectl logs workshop order. Let's say 2. When we look at the logs, we see like starting job, finished job, starting job, and so on. So you see, from time to time, there are some new async jobs started within the app and finished. I have some generator in one of the apps. It sends some backend jobs. Those are fake jobs. So the job is responsible only for starting new lightweight thread and sleep for 30 seconds up to 2 minutes randomly, and then finish within success or failure. But constantly there are new jobs started and the old one are being finished, and that should generate for us some metrics. Yeah. And for example, this is Prometheus UI. This is the Prometheus that is really running inside our Kubernetes cluster. And when I type in here like jobs running, this will give me, oops, sorry. I will look at this later. Jobs running is a simple metric that will show me how much jobs are being run at the time for our apps. I have also another namespace for the apps. That's why you have a lot of time series here. You see, lots. So we don't want that many. So I want to filter only by, let's say, namespace. The namespace will default to only the apps that you saw up to now. And oh, maybe I didn't start the jobs here. Sorry. So let's choose another namespace where we have the jobs. Okay, this one. This I'm generating some jobs. Those are the same apps that are running in different namespaces. And you see there are some jobs running. It's not really visible because we have many instances, like we have 3 instances of workshop order or workshop product. So we'd ideally want to sum by application the number of jobs running. And now you see we have only 3. Workshop view does not run any jobs. And this is the number of jobs running. We see is from 8 to 2, right? At the time. We can also have a look at another metric that this application exposes, like jobs finished count. So let's see how many jobs are finished. So as you see, this is only growing up. This is only going up because once the job is finished, it will not go down. Yeah, because the number of jobs finished will never go down. So what we can do, for example, here, we can sum maybe not by app, because we have also another label here called failed and succeeded, and we can see how many jobs are succeeded and failed throughout the time. And see, you have more than 500 succeeded job and failed jobs. And you can do much more here in Prometheus. Like you can check how many failed jobs are new failed jobs are added per second through some time window. Let's do that. That will be the last thing we'll show here. Like let's take 5 minutes time window and look at the rate. You see, so here we don't count the number of jobs that are failed, either succeeded, but we look at how many per second over 5-minute window of time new jobs are being failed and succeeded. And we see usually there are more succeeded jobs coming than failed jobs coming. What would be a potentially good alert for this? For example, if this graph, this green one, this failed one, will be above, so we have more jobs that failed at this time window than succeeded, then that could, for example, trigger an alert. Okay, that's Prometheus. Yeah, you see, it really works. Our app has some metrics. They are changing over time. When I click execute, you see we have some more data. This is by status. We can also do that by another label, like by application. You see how many workshop product jobs are running. Okay, this is Prometheus. I also told you there will be Jaeger UI. Okay, so let me quickly go back here. And let me first initialize the application with some random data. Maybe I will show you also that it really returns something. Yeah, we have some fruits and vegetables here. Oh, by the way, if someone will ask you, have you learned anything from the webinar and you won't remember anything about the Kubernetes and Prometheus and Jaeger, you can at least tell some fun fact about grapes or mango or something. So at least you have this. Okay, so I've did it. What I also do, and what this app allows me to do, I can, as you can see, send request to the endpoint command/forward. Let me do this like this. And with the TTL set to some value, sorry, I will decrease it to like 3 before milliseconds and after milliseconds. I do that. Then I will do another request, but this time before milliseconds will be like much higher. Okay, and this underneath generated traces and send them to the collector. So let's go to the collector. Oh, I don't know why. Okay, And here is the collector, our Jaeger. As you can see, I can find the traces, and the operation in this case, but probably I have to refresh this. Operation in this case will be called forward. As you can see, I have two traces. So and what this app does, this forward request, it with some TTL, it sent the request to itself, but through Kubernetes service. So if we have 3 pods of workshop view, not necessarily the same pod received the request that sent the request. And if we look here, we see this is our trace. That's what we did. Like, we sent the request to ourselves, and with some before milliseconds, after milliseconds parameters that were responsible for a sleep. So what this did, it make a thread sleep. In short, in simplified terms, it did thread sleep for 5 milliseconds, then sent the request recursively to the same app, and then also did the sleep for some other time. And in the first case, we had 5 milliseconds sleep, then send recursive request, then receive it, then again sleep. You see, we can see everything here. And then after all, we see sleep after 100 milliseconds, 100, 100, 100. And what I did later, by the way, you can see this whole took 1 second, and the second one that I did took 2.4 seconds. Why? Because when we look at this, look, send before took half a second, half a second, half a second, and so on. And when I generated this, I can play with the parameters as well. Let's say 1 and 1. So let's now decrease this, and let's maybe increase also the TTL to much more value. And let's go back to the tracing. As you see, now I have much more traces, and it really corresponds to what happened. Yeah, yeah. All of that you have on GitHub, but yeah, of course, you won't run it from GitHub on Kubernetes, but locally you can do quite the same as I did here. Okay, so let me go back to check if there are any questions. Yeah, I hope you are not lost, because yeah, this is a pretty complex topic, but I think it's really entertaining to be able to have a look. Okay, it really generates the traces. Wow, I changed this parameter. Underneath, I told you how this app works, that it does the sleep. And we can see this sleep time here within the traces. And this really happens now in the real time. It's not pre-recorded, right? It's really, the app really is running in my local Kubernetes cluster. It really sent traces, and this is the result. Okay, let's go maybe to the presentation, and let's ask more questions. So today we ask a lot of questions, but we try to answer them. At least we try to answer them. So can we go further? Did we tackle all of the possible challenges that you will face? No, of course not. I've just cherry-picked some of them to show you. Yeah, I think it was nice to see, but that's not all of those are not all of the challenges. What about advanced routings? What about the deployment strategies? What about service mesh? So let's talk a bit about the deployment strategies. And by the way, let's talk about what is deployment. Let me have a look at the time. It's quite okay. So by default, when you on Kubernetes, when you run your app and want to apply some feature, so you never run your application indefinitely, right? So you have some replicas running. Let's say, okay, you have 3 replicas. I will just draw 3 circles. Let's call them circles on the top of the slide, and they are running. And now you have some critical bug fix, or you're adding a new feature, and what you need to do, you want to have in production 3 replicas, but running the new version, the updated version of your app, right? So that orange one, those orange ones, is the initial state on your cluster. The green one is the final state. And the question is, what happens in between, right? What happens in between? What you can do? I mean, you can, for example, remove everything and run new replicas. What's wrong with this? Maybe nothing, because maybe you have clients only within one geographical zone, and you can, shut down everything for 2 hours, and that's okay. If that's the case, okay, great. But if you can't afford for downtime, then what Kubernetes does by default, it adds one new replica. It waits until it is ready. It's not. It has to be ready, not only running but ready. And then it removes one old replica. Then another new replica. When it's ready, we remove the old. Another new. When it's ready, we remove the old. And that's what Kubernetes does. That's why it's called rolling update, because you gradually add new, remove old, add new, remove old. Of course, you can fine tune it. Another approach would be blue-green. Let's say you have the first deployment, then you apply the second one. And what's going on here is that all of the traffic is directed to the first deployment, so to let's say to the legacy one. And you wait until all of the pods, all of the replicas from the new deployment are up and running. When they are, you switch the toggle, and now 100% is directed to those new replicas, and you can remove the old ones. Also, you don't have downtime. You don't have multiple versions running at the same time, so that's better than it was with a rolling update. But you have an issue with the resources. So at some point in time, you need twice as many resources as you normally need to run your app. With rolling update, it's not a problem, because you gradually add new instances here. You add all new instances. When they are ready, you switch the toggle, you remove the old ones. But that's also a valid strategy. Can we have more complex, more sophisticated ones? Yes, we can. For example, we can have canary deployments that can lower the risk even further. Imagine you have an issue in production. What happens then? Then everyone knows, right? If you have a client, then the client knows, the customer knows that's something wrong. But imagine you have some risky feature. Of course, you have QA, you've tested it, but you're still not 100% sure if how this will work in production. So what you can do, you can send only 5% of the traffic to the new version and 90% to the old version that works perfectly fine. And then, if something wrong happens, there is a fire, but it's limited to only those 5%, right? So this is also the strategy that is sometimes applied. It's more sophisticated, but it can lower risk even further if something goes wrong. You can even not only have to, you're not limited to split the traffic by percentage. You may, for example, say, like if you have, imagine you have 10 clients and one client agreed to test your feature, like, but okay, maybe that client pays you less, but agreed to test your feature. Then maybe you want to forward all requests from that client to the new risky version, but from all the other clients to the normal versions. You can also do something like this. So not only based on the percentage, but based on the type or based on the metadata that the request has inside. Okay, it's the demo time. We're going towards the end. So if it's a demo time, let me have a look if there are any questions. Is there a smart way of combining the rolling update with migrations, data upgrades? The smart way, I mean, the challenges that can come up with those updates is that at the same time you have two versions of your app running. So you may have some feature flags to handle both new body of the request or new endpoints and the old endpoints. You have to do so. Or some of the requests will fail. Maybe that's not really so bad. Maybe you can just retry them. So it's up to you what you choose. But if you're also talking about like data migrations, like the database schema updates, so you have to take care of it on the database schema levels, which, I mean, outside of Kubernetes. So it's not an issue that it's only present in Kubernetes. So you have to be able to roll out the data. So yeah, but working with data migration is really difficult topic, and yeah, we don't have enough time to cover it, and I'm not sure if we would even cover it having a day, all the edge cases that can happen. Okay, let me go to the terminal. I have another service called SM that comes from Service Mesh. Here I also have my apps running. As you can see, most of them has 2 ready, 2/2. It means that the 2 containers are running within each pod. The second container, called Sidecar Proxy, is added automatically by Service Mesh. I won't go into the details of Service Mesh, but what Service Mesh allows us to do, for example, is advanced routing that we'll try now. So let me do the initial load again here and see if I can have some orders here. Yes, I have some orders. And if you look closely at the JSON returned, you will look that, okay, this first part, variant version 2, this is the version of the workshop view app. So the workshop view used version 2 of the application. Then we have value, and we have a list of orders. So this is the first order. It has many products inside, right? And it has a date. And if you have a look, this workshop order was used in version 1, right? And you don't have remarks, you only have a date. And in case of products, so this product was fetched with version 1 and has only the name. The same here, the same here. But for example, this product was fetched using version 3, and you can also validate that by looking at the fun facts that are displayed. For the other version, they are not. So that's how the application differ. If you look closely at the pods that are running, you see we have 2 workshop order pods, and one is with version 1, the other version 2, 3 product pods, and 3 workshop view pods. And how the routing is done here is more advanced routing. It's not the default Kubernetes routing, which is something like it's random split between each of the pods. But here it's not the case. Here I have the service mesh called Istio, and I also have something called virtual service. For all of that, let me now edit the virtual service for workshop product, and let's have a look what's inside. Inside, we have destinations and we have weights. And you see, 90% of traffic is currently routed to the version 1, 5% to the version 2, and 5% to the version 3. Version 1 prints only the name of the product. Version 2, name plus fun fact. Version 3, name plus 2 fun facts. What I will do now, I will route 98% of the traffic to the version 3. You see, I'm online modifying this. Let me save this workshop product. And now, when I ask again for the list of products, you see that almost all of the products, if not all, they have more than one fun fact. You see? You can learn, for example, how much some of them can grow. So it works, right? It worked. Of course, I could change the same for workshop view, for workshop order. They also behave differently, but I won't uncover everything now. So let me jump back to the presentation as we're running slowly out of time. So yeah, again, I have to go outside of the full screen to be able to show you the presentation. Okay, this slide, those are links and sources. Can I copy it? Oh, sorry, but I have to turn on view. Maybe I can copy this. Where, okay, and paste here. Okay. Oh, come on. They're separated by the space, but I hope you can get something out of it. And yeah, let's go the next. So with cooperation with Commerce Training Center, I also teach some other stuff here, not only the one mentioned here. So there are a bunch of courses available, containerization, where you can meet Docker, and also some alternative to that, Podman, free courses dedicated to Kubernetes, where you gradually learn more and more stuff, also connected with Service Mesh, with autoscalers, and the last Prometheus course also has monitoring distributed tracing inside, so something you saw now. There is also a course dedicated to Ansible and to Prometheus itself. There is one more that is coming soon. It's not yet published, probably. That will be a course dedicated to the Rust programming language. This one is upcoming. I think on the Commerce Training Center webpage, you can find this containerization course and Kubernetes introduction. So those top two are already published in English, but basically all of them are available in English. If it's not yet published, just reach out to someone from Commerce Training Center, and yeah, I'm pretty sure we can set up something if you're interested, something outside of Kubernetes introduction and containers. Yeah, we can also do that. So let me just copy those links into the chat. Okay. This last link, this is the GitHub with those apps. So you have here run local directory, where you have everything you need to run this locally through Docker Compose. There is also some instruction here. So you can also have a look at this. And let's go back to the presentation. Okay. I think I only have final slides here. It's supposed to last 1.5 hours, and I didn't know I'm so good at at predicting the time for this, because we have 3 more minutes or 4. So thank you all for coming. Here, if you want to reach out to Commerce Training Center, let me see if I can copy this as well. And because yeah, you can't copy from what I'm sharing, so I'm just copying so you can have access to this. Okay. Let's go back to presentation. And yeah, and that's all. I will probably stop sharing now.